All right. My name is John Williams. I work at Basecamp. If you guys just went to the Shopify talk, some of this might sound familiar. We actually work with Shopify quite a bit and kind of exchange details of our environments and stuff. So hopefully you'll find this interesting too. I'd like to start out with a couple tenets that we have at Basecamp about the work that we do. The first thing that we consider is uptime to be a feature of our application. We include all of our scheduled and unscheduled maintenance in our uptime numbers. So if you go to basecamp.com/uptime, you can see this is actually outdated. It's 9996 on the slide, but it's actually 9995 now because we had downtime last week. Sorry. But the resiliency of our applications is something that's really important to us, and we want to show our customers that it's important to us. The next thing is we consider performance a feature. We monitor performance. I can't give you a number on how many metrics we have, but it's more than I can grasp, and I think that a fast Basecamp is a good Basecamp for our users. And the last one is a little different, but we consider making things simple at Basecamp to be really important. Our products, you don't need a manual to use, and so we like to make things, we call it Fisher-Price simple. If you guys had one of these little phones as a kid, it didn't come with a manual. It just worked, and you drug it around, and it was fun. And that's the way we want Basecamp to work. So now we'll get into the different types of multi-DC deployments. I like to think of multi-DC deployments and DR deployments as like buying an insurance policy. If you buy the nicest policy, it's going to cost you more up front, whether that's in DC terms, that would be time and money, but later down the road, it should end up costing you less. So the first and easiest way to get your DR plan is a cold setup, and that's where all your data is shipped off somewhere else, and whenever you need to get when an asteroid hits your first data center, you can always bring up the second one. It may take a lot of time, you'll have downtime, but the data's there at least. The next step up is a hot data center, and that's where all the data is ready to be served to customers if an asteroid hits your first data center. And that's a big step up from having nothing or a cold data center. And that's actually, I'll get that here in a second. But the perfect scenario is a live data center. And that's where both data centers are serving traffic, both have all the data. So if an asteroid does hit one of your data centers, customers have little impact. And kind of this is how we've done things at Basecamp since I started. Back in 2010, when I started at Basecamp, we had practically nothing. There was no real DR plan. We had a few things here and there that were backed up off-site. Then in 2011, we made a push just to get database backups and object storage backed up to S3 and different places. Then in 2012, we launched Basecamp 2, and that was a big step up for us, both from an application standpoint, and then also it gave us, the motivation to start a hot standby data center project. So in the end of 2012, we started that, and it took a long time, both from having a small team manage that project and try to push it through. So finally, in 2015, we finished it, and we we failed over from one data center to the other and did all the test runs, and it worked. And then later on, through 2015, we launched Basecamp 3, which is our newest version of Basecamp. And when we launched it, it was active out of two data centers. So that's kind of what I'm going to talk about today, is how we got to active out of 2 data centers. So this is kind of an overview of what things look like for us. We have 3 data centers right now, Chicago, Ashburn, and New York City. New York City, you can kind of forget about that one. It's just for our object storage only. And then Chicago and Ashburn are two main data centers. The nice thing about having the third point, it gives us a second path, or actually a third path, but it gives us an additional path to Ashburn over private connections. So if both connections that we have from Chicago to Ashburn were to go down, we could still route through New York City. And this is kind of what our stack looks like. This is really simplified, but it kind of gives you an idea. We have internet, and we use Anycast to route to both of our data centers, to some big IP F5 load balancers, to our Rails apps, and then we go down to Elasticsearch, Redis, and MySQL as our data storage. All right, so now Anycast. That's where I'm going to start at the top. So we wanted to make Basecamp 3 the fastest Basecamp ever. And the best way to do that is try to get Basecamp closer to our users. And Ashburn is just about as close as Europe as you can get in the United States without going to Europe. So we can't speed up the speed of light, so we got as close as we could to Europe without actually going there. And that's why we decided on Ashburn for the second data center. But let's see. So if you're not familiar with Anycast, it's a network routing and addressing topology where packets are sent to the nearest endpoint. They may not be the nearest endpoint in terms of geographical distance, but it'll be the providers will choose the lowest cost path, and which usually ends up being the shortest route. And then, so when users get to your data center faster, they win, and everybody wins. Here's a chart of kind of how things look on Anycast. You can see the red is Chicago, or excuse me, the blue is Chicago, and the red is Ashburn. This is a normal day of traffic. You can see as the day goes on, the Chicago, so the blue line gets heavier as the West Coast comes on because it's closer to Chicago. That's kind of how traffic looks there. We also have integrated Anycast into ChatOps. So, and I'm really sorry this is small. I'm not sure why it's so small over there. So Anycast, we integrate it into our ChatOps. So we can disable Anycast in any of our data centers, so we can stop routing to those data centers just with a ChatOps command. So like Anycast disable Basecamp 3 and RWAsh, which is the name of a data center. And then we can enable it there too. We really try to do as much work as we can in ChatOps. So that's kind of a thing that we try to focus on. When we build a new ops tooling, we try to build it into ChatOps. All right, so next, I'm going to dive into our MySQL setup and how we do that with multiple data centers. So we don't really do anything crazy with MySQL. We don't do any clustering. The biggest thing we do is use Makara, which is an active record adapter built by the people at TaskRabbit. And we use that kind of for our read and write setup. It's kind of read-write splitting. So here's an example of a user that makes a GET request that comes into Ashburn, which is right now is our secondary data center. So the request comes in, it goes through our load balancers, through the Rails app, and then goes makes its MySQL reads from the MySQL replica that's in that data center, which is a replica of what's in the primary data center. We can be pretty sure that that replication will always be up to date. The round trip time between the two data centers is around 20 milliseconds. So we don't have too much fear of the replicas being behind. This is where this is our trick to get writes to be fast without using multi-master or multi-primary MySQL. So let's say a put or post or delete comes into Ashburn. We then will see that request in our load balancer, and then instead of processing that request on the Rails app servers in Ashburn, we actually will ship that whole request over to the primary data center, which is Chicago, and then process it there. The win that we get there is instead of making a series of database calls from one data center to the other, which would be really slow, is 20 milliseconds every time, and if you have 10 database calls, you're looking at a couple hundred milliseconds you're adding on to the request time. So we ship that whole HTTP request over to the primary data center only on writes, so puts, posts, and delete, and then we save all of the additional latency by just shipping it over there. So cache is another, I guess, another simple idea that we have at Basecamp. We started out when we started working on Basecamp 3, and all of our other apps, we use Memcache. And Memcache was good until we started trying to run out of 2 data centers. And there's no good multi-DC support in Memcache. We looked into tools like McRouter by Facebook, and it really didn't fit our needs. It didn't handle the throughput that we wanted to put through it. I guess maybe we were probably trying to use it more than what it was intended for. So we've been long-time users of Redis, and it's always been good. We have good tooling built around it, and we're comfortable with it. So we decided, let's give Redis a shot for caching. And so that's what we did. Redis replication works great, and it's been pretty fantastic. As with MySQL, Redis cache writes go to the primary data center. Reads can come from the secondary data center that's replicated from the primary data center. So the reads are always really fast. Most requests to Basecamp are reads. So the writes, I'm not sure what the percentage is, but there's probably 10 reads for every write, if not more. So if we can improve the speed of reads, we're much better off. Redis also gives us the ability to snapshot our caches and then perform maintenance on servers or anything like that. So the next tool that I want to talk about that we've done, that we've built, is a tool called SwitchedOur. And it is a framework that we built to check the states of systems. It's written in Ruby. It's not open source yet, so it's considered vaporware right now, but I hope to have it open source sometime soon. And this is kind of how it works. In the simplest form, SwitchedOur can just be made up of states. So is SSH available? It could be CPU load or the state of a service, the existence of a file on a system. Then the interface with the servers, it can be done over SSH. That's usually how we've used it. And then systems can also be built up from the states. Systems can contain as many states you like. So if you see in the second column here, we have server database 1. We can check if its database is available or if MySQL is running. Then the services can also include subservices. So we have the database cluster. It can include all the database servers that include all of the checks. So if one check fails, then it just bubbles up through the services and through the all the way up to the top service. So here, I kind of got a demo here. I can't really, it's not very visible. But what you'll see, or I hope you'll see here, is this is a run of our pre-flight checks for our database, for our data center failover. So if you'll see when this runs, you'll see there's one red check in the middle that's failing. So it'll continue to run until I fix the check, and you'll see when I switch back over to the other tab, it'll turn green, and then the pre-flight checks will exit out. So it will continue to run until all the checks pass. So we run this at the beginning of our data center failover. So whenever we kick off the failover, it will run, and when all the checks finally pass, if they do pass, then it'll continue on. And we run that multiple times throughout the failover to determine the state and make sure that everything is failing as we expect, because the whole failover is scripted. So the next tool I want to talk about is called Intermission. It's an open source tool that we've built, and it uses an OpenResty, it's an OpenResty Nginx plugin. It's written in Lua. Its purpose is to pause incoming HTTP traffic. So when we are failing over between data centers in a test, we can use Intermission to pause the incoming traffic at the Nginx level, so behind the load balancer. And we can hold that traffic there while we do the work on the background to switch, like we're switching MySQL replication or switching Redis replication. We can do all of that in the background while Intermission holds those HTTP requests at a level higher. It's got an HTTP interface. You can enable it, disable it, and check the status all from an HTTP call. And like I said, it's open source. You can see it on GitHub. And we use it also for database maintenance. So anytime we need to take down a MySQL server and switch a replica to a primary server, we can use Intermission to pause the traffic on the front, switch everything we need to in the background within like 30 seconds or so, and then we unpause the traffic. Traffic goes through. Customer just, whenever their request just look like a long HTTP request, so it's not really impacting the customers. No 500 errors. The one trick is you do have to make whatever you're doing on the background needs to be done quick before you hit an HTTP timeout. So that's something to keep in mind. The next tool I want to talk about is MySQL role swap. And this is a tool that I wrote at Basecamp, and it plays along nicely with the last tool, Intermission. So we use it to handle the promotion of a replica, MySQL replica, and it handles all of the switching of replicas and primaries. It's written in Ruby. It uses state machine and active record. It has a YAML configuration. It's pretty easy to figure out. It has optional integration with Intermission, and it can also manage floating IPs. For the case of data center failover, we don't use floating IPs because we don't float IPs between data centers. So that's an optional part of MySQL role swap. It's fast. The way that it works is basically we take when you initialize MySQL role swap, we do some pre-flight checks to make sure that the cluster state is kind of what you would expect. So there's a primary, there's a replica, they're replicating properly, and then if you have intermission enabled, we'll pause traffic. Then once traffic is paused, we use change master and change the replication around. Then we unpause traffic and then reset up the new replica from the primary, or what became the primary. So I guess kind of putting this all together on what Basecamp failover, what it ends up looking like. So this is kind of this is a rundown of what we do to fail over from one data center to the other. There's first we run as we saw, the SwitchedOur pre-flight checks. Then we do a process of stopping all of we disable all the crons and the background jobs that may be running in both data centers. Then we run the SwitchedOur mid-flight checks, and that verifies that all of the crons and the jobs are dead, and we're not writing to databases that shouldn't be written to, and that sort of thing. Then we enable intermission to pause traffic. We use MySQL role swap to promote the secondary data center databases to the primary, and we do the same thing in Redis. We just script the Redis promotion of the primary, and then we publish DNS changes. So everything that we do, all of the applications connect to their backend services via CNAME. So that's how we handle it. So we publish the DNS changes that points to the new databases. We restart all the Rails instances, and then we disable intermission. That allows the herd of traffic all the way back through. All the requests that were paused end up getting processed, and then we're considered failed over to the second data center. Then we enable all of the crons and the background jobs, and then we do some post-flight checks, which is basically the reverse of the pre-flight checks. So we're checking to make sure that the state at the end of the failover is the exact opposite, basically, of what it was when we started. And that, I went kind of fast, but that is what I have about how we handle failover. I would love some questions or discussion about how we do things. So if anybody has questions, I'm all ears. Yeah?
How long does that process typically take between pausing and resuming traffic for intermission?
We usually try and go under 30 seconds. That's our goal. So because we will start to see HTTP timeouts going much longer than that. I think the longest pause that we've done is around 2 minutes. We also all of the way that intermission holds the traffic is in Redis. So all of those HTTP requests get queued in Redis. So I mean, we can't go over our queue there either. You know, we don't want to blow Redis up with a ton of requests. So that's kind of how we like to keep it shorter. The shorter, the better. Yeah.
How do you deal with, or where are you planning to deal with the true disaster situation where you might not be able to connect to what was your primary data center?
So we also have cold failover scripts written, which basically it kind of just forgets about the primary data center and just does the work to promote the secondary data center. So like MySQLs that were read-only, they will become read-write. And I think at the top of our documentation for those scripts, it says only run these scripts. If you don't run it, you'll lose your job. And if you do run it, you weren't supposed to, you'll lose your job. So it's kind of it kind of sets the tone that only run this if you're going to lose your job if you don't run it. So.
Right. So what do you do when what was your primary disappears for a while, like it comes back online? Do you have anything to stop that? Any traffic again?
So we can determine or we can decide what data centers take routes. So in all of our, if a data center goes offline, and we really haven't had a data center go offline for a long period of time, but that decision has to be made on like what is a long time, like what do we declare as bad enough to cold fail over to the other data center. So that's kind of a tough problem to solve. And then whenever that once you do like an asteroid hits one of them and it comes back online, we can decide if we want to route to that or, if we just leave it dead, and that's something we can choose. So, yeah.
The data center that went down doesn't know that it went down. When it comes back up, its database is still in read-write mode.
Right, and we just right. Well, in that case, we just don't, and we just remove the announcement for our Anycast announcement from that data center, or we decide that we once it if we decide we don't want it to come back up at all, we don't announce any routes from it, and we only get through it through a through our yeah.
So, do you pause requests when you do failover, right?
Say that again?
Do you pause the requests in Nginx when you move data centers?
Yes.
And so,
Just for our test runs. So
Okay.
because we don't want to, we want our test runs, we want to be able to do test runs as frequent as we need to,
Okay.
and we don't want it to be customer impacting if we can avoid it.
so for the real move that you don't pause the request.
Right. If we did a real move, we could. But if a data center gets blown off the map, by an asteroid or something like that, we don't really have the ability to pause. So there's nothing automated about the pausing. It's just for our failover scripts. So let's say that we wanted to take a data center down for Basecamp 3. We could use these scripts that pause traffic and shuffle them all over nicely rather than just stoning a data center in the head.
Yeah, so for what we do at Shopify, actually, it'd be really nice if we were able to pause the request in the Nginx. We do our DC failover and then forward those requests to the new data center.
Yep, then that's exactly what we do.
Okay, that's great.
Yep.
Yeah, thank you.
Yeah.
How many requests can you queue up in that intermission?
As big as queue as you have that can hold the request. So the downside is the more that you queue, those HTTP requests are just going to get, you could end up DOSing yourself by, if you pause so long or pause so many requests that you don't have the front-end web capacity to handle those, you could end up DOSing yourself if you're not careful. So it's whatever you can handle and however much cache you have to handle those, the queuing of those requests.
How much traffic are you getting in Basecamp
Here. I think usually we do the maintenances at night, so I'm going to guess at a maximum probably 5,000 requests per minute. At a minimum maybe a couple thousand, and it could fluctuate. But we kind of build the tools to be able to handle at the upper side of traffic. So we should be able to handle 10,000 to 15,000 requests per minute in intermission. Yeah.
Do you have a sense for what percentage of your requests are initiated by users in the application that are actually waiting for a response in the moment versus like part of a background running process or timeout or something like that? But the actual user experience of the failover, whether they're also waiting for the 30 seconds period, that kind of thing?
I don't have any hard numbers on that. Most of the requests that Basecamp 3 get, we just launched the API a few weeks ago, so it's not a lot of them aren't API requests. Most of them are user initiated requests in a browser. Now, how many of those users sit around and wait for the 30 seconds? I don't really know, before they hit the X, and refresh. But usually by that, by the time that someone would be like, this stinks, Basecamp ain't loading, hit the refresh button. Usually it's done by then, so, it's kind of problem solved. And to be perfectly honest, we have gotten very few we've probably done a half a dozen production failovers now, and we've gotten very few customer requests. And usually we have pretty vocal customers on when stuff's down because Basecamp is their livelihood for their business. So, usually we hear about it and we haven't heard too much. And that's why we kind of choose, when we do test failovers, picking the right time of day, the right time of the week. Don't do it middle of the day. We've wanted to show that it works, under production load. It's really tempting, but we haven't done it yet. The other thing too is in the U.S. time, don't choose Sunday early morning because you're gonna, affect Europe Monday morning, or even if you do it Monday or Sunday night, you're affecting Australia when they're coming online for the week. And Monday mornings are not a good time to take out somebody's project management software. So, yeah. No, so here, I can go back a few slides. So what we do is we don't actually replicate the request. We just direct it somewhere else. So whenever, let's say it'll be a write request, so a put or post or delete, comes into the secondary data center. Instead of processing in that data center, where it will be slow because we're going over that internal link at 20 milliseconds each request. So those MySQL queries, are taking, at least 20 milliseconds each, and we're adding, if we have 10 of those in series, we're looking at 200 milliseconds. So instead of doing that, we just ship the whole HTTP request over and let it process in the primary data center where it can do all those queries fast on the Rails app servers there and the database servers there. So, and that would, the idea of doing multiple, if we did do something like replicate the requests to multiple data centers, then you end up with you could end up with a split brain situation of trying to write to two data centers with the same data, and you got two versions of the data now. So we always try and keep the state. The secondary data center is always, even though there's a MySQL primary and a secondary in the second data center, it's always, while it's secondary, it's always read-only. So, and same way with the Redis instances there too. Any other questions? Right, so that is something that we actually kind of, fought over before we use this setup, was if you do a write into the primary data center, then it takes time for that replication to happen to the second data center, and then we have to be sure that the second data center is up to date. And really, it hasn't been a problem. It's the 20 milliseconds between the two data centers is fast enough that by the time that someone does a read, it's fast enough that they're going to go to get the right data. So what we thought was, what we thought was going to be an issue, we really beat our heads against it, ended up not being an issue at all. So, and that being said too, the links between our two data centers are two 10 gig links. And then a third if those go down. So, we have a big enough pipe to handle whatever we want.
It's usually not about the throughput, but about MySQL itself. You do an alter table, you need log within MySQL, and replication stops.
Right.
And somebody clicks a button, write goes to one data center, the page refreshes.
Yep. And part of that too is making sure that your writes are fast. And you're not doing table locking and alter tables and stuff like that while you're in production. We can get on a topic of MySQL, our MySQL setup, which is huge monolithic databases. But yeah, we'll save that for later over beers. Yeah.
Have you done a write failover at all, or have you only done read-only failovers?
So. What do you mean by the write failover?
So right now you're directing your writes back to your primary in Chicago.
Correct.
Have you ever tried to fail that traffic over to your read-only data center?
Yeah, so that's when we do the failovers, that all switches. So then the second Ashburn becomes the primary, and then any writes that come into Chicago get directed to.
Okay, so
So it's all done via an I rule. So basically, when the request comes in, if it's a put or post and it's in the secondary data center, or what's the secondary data center at that point in time, then we say, okay, you need to get shipped over to the other data center. And actually, the actual switching part of that is all done via a health check in the app. So the app knows if it's in a data center that's the read-write data center or not. So we use a Rails plugin that I didn't mention in here, but we use a Rails plugin called EasyMon. And basically you can monitor anything in your app, any endpoint, and we basically create endpoints that we can monitor internally. And then basically we just set a flag in the app if that data center is read or write only. So, anything else?
What do you do with database migrations? How do you handle that? I imagine you have a lot of them.
Yeah, so I think in Basecamp, Basecamp 2 is probably the largest database, which is probably, I think now we're probably getting closer to 2 terabytes. The largest table probably right around 1 terabyte. So schema changing that table would be probably like 48 hours or something like that. We tried not to do too many schema changes on the really large table. Usually we try to work a way around it. But usually when we do need to do schema change, even on smaller tables that may take 2 or 3 seconds, we use PT online schema change from the folks at Percona, and it's been pretty rock solid until Rails 5 with foreign keys. That's added another layer of complexity because the foreign keys are still referenced in the old tables that PT online schema change creates. So that's kind of been a tricky point with PT online schema change. But there's also, I believe GitHub just came out with a new tool also for schema changes. I don't think we've done too much exploration into that yet. But there's also always the older way of adding columns to a table, and that's perform it on the replica, and then you swap the replica in. And yeah, but you can't delete columns. You can only add columns. So that's kind of a tricky spot. But PT Online schema change has always served us pretty well. So anybody else? Well, thank you guys very much. There is I left the links here for the 3 tools. That I talked about today. There's another one that I just mentioned was EasyMon, which is just basecamp.com, or excuse me, github.com/basecamp/EasyMon, which is also open source. So, all right, thank you very much.